Welcome back. In this lecture, we will cover a couple more examples of differentiability. This time, we will deliberately cook up some really complicated looking functions, to which the limit definition no longer gives easy answers. And we will see how we can make use of the epsilon delta definition of differentiation in this setting to help us demonstrate the differentiability of a function. Let's get started. The first function we will treat is a function defined on the interval from -1 to 1. It has the following piecewise definition. When the absolute value of the input is between 1 over n plus 1 and 1 over n, where n is a natural number, we set the output of f to be -1 to the power n divided by the quantity n plus 1 squared. And we complete this definition by adding that f of 0 is 0. Notice that every single number between -1 and 1 are accounted for in this definition. The question is the function f differentiable at 0? Before getting started, it may be helpful to visualize the function. Here, the function f is plotted in red. I only show the portion of the x-axis between around 0.15 and 1. As you can see, between 1/2 and 1, the function outputs -1/4. Between 1/3 and 1/2, the function outputs +1/9. Between 1/4 and 1/3, the function outputs -1/16. Between 1/5 and 1/4, the function outputs +1/25, and so on. So as we approach the origin, the value of the function appears to approach 0. As mentioned before, because of the complicated piecewise formula that defines the function f, the limit definition is not ideal for treating whether the function is differentiable. Instead, we'll show how to prove that the function f is differentiable at 0 using the epsilon delta definition. Let's go through the proof step by step. We will show that the derivative of f at 0 is, in fact, 0. In step 1, we just recall what is our goal. We need to show that the difference between the function and its best linear approximation can be made arbitrarily small. Since my goal is to show that the derivative is 0, we can set m, the slope of the linear approximation, to be 0. And the center C is also 0, since this is the point at which we wish to compute the derivative. So the inequality we hope to prove simplifies to f of x is less than epsilon times x. In step 3, we get started with the actual proof. Let epsilon be positive. By the Archimedean property, we can find some k such that 1 over k is less than epsilon. I will take delta to be exactly 1 over k. If the input x were to have value between 0 and delta, since delta is equal to 1 over k, and x is not 0, the input must belong to one of those intervals for some n at least as large as k. On this interval, taking the absolute value of f yields the value 1 over n plus 1 squared. Since on this interval, x is always at least 1 over n plus 1, this shows that the value of f is no more than x divided by n plus 1. This turns out to be less than x over k, since k is less than n plus 1. And by our choice of k, we know that f of x is less than epsilon times x. This is exactly what we need to show to prove, using the epsilon delta argument, that f has a derivative 0 at the origin. Our second example is another piecewise defined function. This time, the function is separately specified for rational and irrational inputs. For rational inputs, the function is a cubic function x cubed plus 2. For irrational inputs, the function is given by 3 times x. We are asked to prove that this function is differentiable at x equals 1. As before, it is useful to take a look at the plot of this function. At a glance, it looks like there are two curves plotted on this graph. In fact, it is one graph. The upper curvy portion corresponds to the rational inputs. The lower straight portion corresponds to the irrational inputs. Since both the rational and irrational numbers are dense in the reals, on the graph, both the rational portion and the irrational portion look like solid curves, even though in reality, both curves are very holy. By inspection, we see that if the function f were differentiable at x equals 1, we would expect the derivative is equal to the slope of the straight piece, which is given by f of x equal to 3x, and so we expect the derivative to equal 3. Let's prove it. Again, since we have a complicated piecewise function, we will use the epsilon delta definition instead of the limits definition. We start by doing some algebra. For the epsilon delta definition, we need to compute the difference between the function and its best linear approximation. Plugging in that c equals 1 and slope m is equal to 3 in accordance to our expectations, we see that after subtracting the function 3 times x minus 1 minus 3 from its definition, the difference is again only piecewise defined. When x is rational number, the difference turns out to be this expression we see between absolute values. When x is irrational, since the function is linear for irrational inputs, we see that, as we may expect, the difference between the function and its best linear approximation in fact vanishes. So this shows that the worst case scenario is what happens when x is rational. So we can say that regardless whether x is rational or not, the difference between the function and its best linear approximation is always no bigger than the quantity x cubed minus 1 minus 3 times x minus 1. This we can factor and simplify to become x minus 1 quantity squared times x plus 2. Remember, we will have accomplished our task if for every epsilon positive, we can find a delta positive such that if x differs from c by no more than delta, or in other words, x minus 1 is no more than delta, then this polynomial is no more than epsilon times x minus 1. The first bullet point here captures just what I just said. Now, since we are working with a limit and hence only interested in what happens when x is not 1, we can divide both sides by x minus 1. This means what we need to show can be simplified to proving that x minus 1 times x plus 2 can be made smaller than epsilon when x minus 1 is less than delta. And so now we are finally ready to choose our delta. I will choose delta to be the lesser of epsilon over 4 and 1. The reason is that if I choose x minus 1 to be less than 1, then x plus 2 can be no more than 4. And hence, x minus 1 times x plus 2 is at most x minus 1 times 4. And if we use that x minus 1 is also less than epsilon over 4, we can conclude that the product has to be less than epsilon. And since our earlier reductions show that once we prove this inequality, we are done, this is enough to conclude that the function f is differentiable at 1 with derivative 3. Okay, that's it for this lecture. See you next time.